1964. Okay, so let us find the longest valid obstacle course at each position. Let me read the problem. Okay, so there is an array called obstacles, and each of the element is the height of the ith obstacle. Okay, so find the length of the longest obstacle course. What does it mean by longest obstacle course? Okay, you should choose any number of the obstacle between 0 and I inclusive. You must include the ith obstacle in the course. Okay, you must put the chosen obstacles in the same order as they appear in obstacles. Okay, so this point means that it should be a subsequence. Every obstacle should be taller than or the okay, so it should be larger or equal to the obstacle before it. Okay, so it is I think this problem is asking for the length of the longest increasing subsequence. Okay, just translate the numbers values to obstacles. Okay, so let us check any limitations. Okay, so if it's if the I am not sure if this works because the solution that I came up should the time complexity will be the square of n, so it will be like the 10 out of 10. Not 10 out of 10, but 10, and it will be the 10 power of 10. I think it's a bit large, but yeah, because for the longest increasing subsequence, these kind of problems, there are 3 solutions that I can come up with. 2 of them are the big time complexity will be big O n with the power of 2, and the other solution that is greedy plus binary search. It will be the time complexity will be big O n, but I don't think it can address this problem because this problem wants the length of every position, and the greedy approach it only counts the largest one. And yeah, so I don't think that is possible. So we will just try for the 2 solution. And the first one, it is it will be, so when you will be like so first of all, if we choose the last element of the obstacles, then the problem will shrink into finding the longest obstacle in the rest of the subarray. So yeah, so for example 1, if we choose, so for so when we choose the last element 2 for the as the end of the subsequence, then we will have, then the problem will be finding the rest of the subsequence in the rest of the subarray, that is from index 0 to index 2. So we will and the next element of it will have to be smaller than 2, the previous element that we select. So yeah, so I will define the problem as I will use the depth first search approach, because it seems like a tree structure that you have many options to select from, and then if this option is smaller than the previous one, or smaller or equal to the previous one, you can go deep to move on to the next next option. So for like 2, if you can select 2, and you will start at the option of this subarray, and then there is only these 2 options that you can select. So we will go down to see if we select 2, then we will have only 1 for the next, and if we select 1, then there will be no option. Yeah. Okay, so it seems like a tree structure, so I will use a depth first search first. Then yeah, if there's any optimizations, then we can go for it. So I'll have div as I, and I will be the index of the element that we selected. So I will define it as the length, the longest length, the longest length, the length of the longest, okay, the length of the longest subsequence, longest non-decreasing subsequence, that the length of the longest non-decreasing subsequence in subarray obstacle 0 to I, even the selected value at index I. And we can put this the result of DFSI to the output array. Okay, so what is the equation of the DFSI? It will be trying to find the maximum of DFSJ, which is from the subsequence. there are, yeah, we can see the rest of the array. We will check the rest of the array, the sub-array, which element is smaller or equal to I, to value at index I. So it will be like obstacles J is smaller or equal to obstacles I, and it will be plus 1 because we already selected the I. Okay, so we define DFS, and the time complexity is big O n with the power of 2. Yeah, because we loop through we have to loop through every index I. To check if we started from, yeah, we can, because we can start it from any index in the obstacles, and that's the result that that the problem wants us to find. So yeah, we will have it like this. And we will return the maximum. There is no edge case, there is no boundaries problem, because if I is smaller than 0, it will not run the for loop. But we have to add a default value so that this max will not be empty. So we'll be copying like this. We will add a default. If the I is 0, then it will be default to 0. Yeah, the value here will be default to 0. And then we will return. We don't have to. Yeah, we will have like DFSI. For I in the range of and obstacles. Yeah, I don't like this. I think we will done some dry run. Let me dry run the thing. Oh, okay. Yeah, it should be catch that this. Try it again. Okay, let's try it now. So for like if we use one this example one, it will be so we will first, the I here will first be 0, so it will be DFS 0, and for 0 it will default to 0, and it will return 1 because it has a length of itself. So it will have 1 here, and then we will have, for I here it will be 1 now, And then for 1, it will be, the j will be started from 0, and if obstacles are at 0, it is 1, which is 1. Is it smaller than obstacles 1, which is 2? Yes. Then we will go into df as 1. And since df as 1 is 1, we have already counted before, then it will be 2 now, also because added here. Then we move on to I, when I is 2, which is value 3. When the I is 2, okay, here is 2, j will start it from 0 again, and for dfs 0, it is 1, right? It is in the array. And for, oh sorry, we have to check first if obstacles at 0 is, which is 1, is it smaller than obstacles at 2, which is 3? Yes. So it will have df as 0, which is 1. And then it will have and you will have to maximize the whole thing. So then we will have j will be 1, and then we will do the condition check here. So if obstacles at 1, which is 2, is this smaller or equal to obstacles at 2, which is 3? Yes. So dfs 2, we will have dfs 2, and then it dfs 1, and which is 2 for the value. And since 2 is larger than dfs 1, dfs 0, which is 1, we will have the 2 plus 1. So answer for dfs 2, it is 3. And then we will move on to the last one, which is 3 for the value I. And for dfs 3, j will start it from 0 again. So let's check if obstacles at 0 is smaller than obstacles at 3, which is 2. Yes. So dfs 0 now is 1. And for j will be 1 now. So if obstacles 1 at 1, which is 2, is this smaller or equal to obstacles at 3, which is 2? Yes. So we have dfs 1, which is 2. Okay, so let's move on to the j, which is 2 now. So let's check if obstacles 2 at 2, which is 3, is this smaller than obstacles at 3, which is 2? No. So we will not have dfs 2. So the only value that we have is 1 and 2. So the maximum is 2, and then we will add it up, this 1. So it is 3 as well. So yeah, it's correct. Then let's check if it is. And let's wait for if it's working. Okay, that's for now. I wanted to first talk about the other solution, that is we can, because it is about finding the longest increasing subsequence. We can also sort the array, sort obstacle array, and try to find the common the longest common subarray with the between sorted and unsorted array. Time complexity will be big O log n plus n square. It's log n. It's okay. I'm not sure if it's working. Okay, so this might be, I don't know, too much time. Let's translate to the dynamic programming, translate to for loops. So it will be, we'll first create an array to catch the value that we have already calculated. So it is, we will just call it like makes sense. And we will have n as the length of obstacles, and this will be n, and I will have like a 0. Okay, so for each value in the obstacles, max then will be, oh sorry, okay, we don't need this. So um for each value in obstacles, its maximum length of the longest non-degree subsequence will be max of the previous results is from that is the previous results before before index I, and also it should meet the condition of the value has to be larger than the obstacles J. And if I is 0, we will default to 0. We also have to add up 1 because we already selected the index I, the value. And we will return max then. Let's see if it's running faster. Oh. Something went wrong. I'm not sure what it is. Let's check. Any translation is that's a hair. Okay, let's submit. Hope we can pass. Okay, I'm thinking of, so at the beginning of the video I gave up the greedy solution thing. Is that I think that might be wrong. I should use it. Yeah, I said that because this problem should find the length of each element, so it is not suitable for the greedy approach. Because for okay, so yeah, we can still use it and use the gradient approach, but kind of different is that we have to find every we will try to we will find the index, like before we have a tell array that kept track of. Yeah, I think for every time when we loop through the obstacles array, we will maintain a tell array that stores the last element of the given length. So when there is a new iteration, we will try to find where can the value sits. If it is larger than the last element of the array, then it will be append. Then then yeah, then the value will be 3. Oh no, sorry. I think I will write it down, it will be easier. So before we will have, so in the previous questions, the tail is like tail, we will have an array tail, and for tail I, it is defined as the last element of the longest increasing, the longest non-decreasing subsequence that has the length of I. Yeah, so it's like this. So but we will change it. So when we maintain this array, I think we will maintain another array that is the answer. So for every iteration in the obstacles, for the obstacles loop, we will use the bisect right function to search for the last element in the tail, to search for the last element that is equal or larger than the current value in the obstacle. So that indicates and the output, the bisect right output will indicates the position of the value if we want to insert it in tail. And it will be also, the index will also be described as the length of the length. Yeah, it will be also described as the length of its non-decreasing subsequence. Yeah, so for so I think I will do it a for loop for obstacles, and for each obstacle value I will use the bisect right to find its index, its insertion index in tail, and I will keep the index, and it will be the answer. It will be, yeah. So first of all, I will enumerate the obstacles, and index will be biceps, right? Tail, input for tail, and there's no definition for tail. Tail will be an empty array at first. It will be binary search for the target value. So okay, so if index is smaller than the length of tail, then it will have to replace the value in tail. Else, it should be append after the last element of tail. So it will be like this, and I will record it as this. Okay, so the answer, I want it to be the same length of obstacles, so it will be like this. I will first give a default value like none, and it will be the length of obstacles. So answer I will be index. Let's see if it's correct. Is it tail? I don't think it's tail. There's a small mistake. Oh, I don't think so. Okay, I still do not understand the solution. I have no idea why it is. Okay, so I found it. The mistake is forgetting to plus 1 for the return index of the bisect, right? Yeah, so that's all for this problem.